Hi, my name is Jesus Galindo, and this is my hairpin filter design presentation for EE425 Midterm 2. First, to go over the general design process, I selected 750 megahertz as the target center frequency for the hairpin bandpass filter, and I inputted that value into a microstrip hairpin generator, and then used that geometry in KiCad, added a board outline in the bottom ground plane, and then exported those Gerber files and imported the copper layers into ADS to do the RF Pro simulation, and used that to view the S parameters and near field behavior using a two-layer PCB stack-up that would be compatible with the OSHPark board fabrication process. So here is the initial hairpin geometry. As you can see on the left, that is the microstrip hairpin filter generator. And using a center frequency of 750 megahertz, the hairpin should be 53.162 millimeters. And I was able to just output that KiCad footprint and input it into, well, KiCad, and then from there into ADS. So the board outline was set to about 50 by 80 millimeters with two layers, the front copper layer and the back copper layer. And the front contains the hairpin resonator and two feed pads, as you can see on the board. And the back copper layer was a solid ground plane for the microstrip. And I put a silkscreen on top with just basic labeling for the ports and what the filter is, as well as my name. After that, I was able to simulate it using RF Pro, importing the front copper layer as the top conductor and the back as the bottom, or I guess the front and back, yeah, bottom conductor, and we're specifying the size of the board using the edge cut layer, and putting two 50 ohm ports at the input and output respectively, and referencing the bottom copper layer as ground. So the information on the left is just another breakdown of the two-layer microstrip setup, which I went over earlier. But I did an initial S parameter sweep just to get very full view of the behavior, both at the intended frequencies and at much higher frequencies, to see how that behavior would break down. So I did from 500 megahertz to gigahertz, and then did a more focused sweep around the passband between 500 megahertz and 800 megahertz, and the results were good. And here are the simulated S parameter results, showing in S11 minimum of about negative 32.5 dB at 0.763 gigahertz, which is 763 megahertz, and an insertion loss of 3.69 dB at 758 megahertz, which is reasonable given the non-ideality of the board. And now here is the sweep between 500 megahertz and 1 gigahertz. As you can see, the passband is close to the 750 megahertz design frequency, with the best transmission marker of about 3.69 dB near 757.8 megahertz. And you have good return loss occurring in the same frequency region, and as seen in the previous wider sweep, the higher frequency response can be attributed to microstrip behavior. And now here are the E-field and surface current density results. We weren't required to put in the surface current density, but I think it illustrates the behavior of the filter very well. But first, for the E-field, you see coupling around the ends of the hairpin microstrips, and as you can see that it's functioning properly. And for the surface current density, you can see the current flowing along the resonator arms at the passband, so indicating that the filter is working as intended. fondly to go over what was achieved. A 750 megahertz hairpin filter was generated, laid out, and simulated with the design confirmed using RF Pro simulation, and achieving insertion loss of approximately 3.69 dB near 757.8 megahertz. That was near field and current plots were generated to confirm resonator excitation and coupling, and they did confirm them. And all the files were exported to OSHPark and printed and fabricated, sorry, and will be received shortly. Thank you.